Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today I want to talk about a very important principle that applies to a lot of different switching power supplies, but we're going to demonstrate it with this boost circuit that we've been using, this boost power supply, okay? You might have kind of caught a glimpse of what was going on in the last video. I was trying not to show what happens when you go from discontinuous mode of operation, which I've kind of been showing, to the continuous mode of operation. And what are those? Well, when this inductor fully discharges before the next cycle, that's discontinuous. It kind of ran out of juice. I call it running dry. So it fully charges, and then say it fully discharges, and then right at that point it charges again. That's kind of a boundary between the other mode of operation I want to talk about, continuous mode of operation. Continuous is when that inductor always has current in it. And what that'll look like is that you'll still get this, you only have so much ramp time and so much time to, ramp down, right? And when you get that point where as soon as it ramps down, it starts to ramp up again, you kind of maxed out the ramp, okay? So that part doesn't change. But what happens is you build up a DC current in this inductor where it's always conducting current. So what will happen is you'll see this level of DC current underneath that sawtooth. And so you got a DC value of current and then this sawtooth riding on top of it. So it just kind of floats up above. So that's the continuous conduction mode. Now, some power supplies, they're designed to operate in that continuous conduction mode all the time. And why? Because the peak to peak isn't your full current value, right? So, so the average value of this peak to peak charge, if let's say it ramps up from 0, fully charges, fully discharges, hits 0, and then starts immediately again. That's the critical mode of conduction, or the boundary condition between continuous and discontinuous, because it really did run out of current, but then it's charged right away. So that's the boundary condition, or the critical mode of conduction. The other two are continuous mode or discontinuous. Now the thing with, let's say, discontinuous, the worst case scenario is when you're at a critical mode. By worst case scenario, as far as the peak to peak current value. So it's fully charged and fully discharged. The average value of that current is half that value, half the peak to peak. Your components are seeing very high peak currents. Okay, so you might want to operate in continuous conduction mode. In continuous conduction mode, then you can have this peak to peak at a smaller peak to peak amplitude, and you can provide more DC current. So now you're not seeing as much ripple current on your capacitors, on your input and output. You're not seeing as much high peak currents through your inductor or your transistor. It might be easier to filter, might be easier to run clean or have a nicer output. Well, okay, so why is that hard? Why don't we always operate in continuous conduction mode? Well, because if you're in continuous conduction mode, and let's say your load drops down to 0 or close to it, if you have a load that has a range to it, it's hard to maintain continuous conduction mode because you might fall out of that and go into discontinuous. Okay, so if you operate continuous, you kind of like to stay in that range. If you have a load that's going to vary not a whole lot, then it's easier to stay in continuous conduction mode. So let's say that you are going to operate it down to 20% load to max load, 100%. Well, then you could design that inductor so that it always had current in it at 20%, and then at your max load it has more DC. But you could design it so you have a minimum amount of DC at your 20%, and then you can design it that way. But it's really hard to design if you have a no load to full load. And even that 20% to max load, if it's a high current, that could be difficult to do. If it is a high current and you're discontinuous, you're going to have really high peak-to-peak currents. So there's a lot of things in play here. Okay, so then maybe the best of both worlds is, you know, kind of like what this guy might do, is have it operate in continuous mode after a certain level, and then below that, let it go discontinuous. What the heck? And, you know, that's often done. Now, the trick is, though, is the control loop. The control loop is different for continuous versus discontinuous. It's actually easier in discontinuous mode because you fully charge it up, you fully discharge. Hey, you're done. I did my thing, I know where I am, and I start over. And I can only go so wrong because if my load changes dynamically somewhere in there, okay, next time I'll try harder. So you kind of see what I mean. It's you know, for the control loop to go out of control and go crazy, it's not as likely, because it finished one cycle, it says, okay, next cycle I'm going to try this. Oh, that didn't work out so good. Okay, next cycle I'll do this. It's not like where, let's say you're in continuous conduction mode, you've got a lot of DC current, and then all of a sudden you go down to no load. Maybe all of a sudden the load disconnects, cable breaks, or you know, whatever. All of a sudden you go discontinuous. Well, then now you're like, wow, I got all this energy and nowhere to go. I mean, it can actually zoom up and take out your transistors. So you could have a problem like that in a situation where you went from full load to no load suddenly. So your control loop, it would have to be a lot more robust to make sure that you're okay during those situations. So control theory, you know, is a little tougher at the continuous. Not tough, but just a little bit. But going from continuous to discontinuous, now it gets even a little bit more complex. Not a big deal. I mean, we can do it. This guy does it. So, you know, just things to consider when you design, which are things we're going to talk about. You're going to see today, I'm going to show you some waveforms on my book, and we're going to show you this guy in action on the scope. So after today, you'll have a lot better idea of continuous and discontinuous, okay? So it's just something presenting today. We're going to talk about more, and we're going to end up designing this guy pretty quick here. We're kind of running out of topics as far as all these discrete topics about this converter design, which, like I say, apply to a lot of other converters. So once we really hammer this guy home, you'll see this parts of this repeated in other converters. We talk about them, and so that conversation, those things will go quicker because we've already done it before. And as you see, basically repetition, you know, it'll start soaking in, and you'll have a really good understanding as time goes by. So let's just do this, and let's jump over here and take a look. All right, let's do it, guys. Okay, so this is just a refresher of the boost circuit. We have our input source, we're going to, in this case, be around 12 volts. And we have our control circuit that turns on and off our transistor, which I'm showing as a switch here. We have our inductor. So the way this works, just go over this again, is when the transistor turns on, charges up the inductor. When it lets go, it discharges into the output, and it boosts the voltage up. So we'll see the voltage get boosted up here, and then it charges up the capacitor and supplies power to the load. So when the transistor's on, it's kind of like we have two circuits, because this is shorted. Diode's reverse bias, so basically he's gone, and we have these two circuits. So just, you know, quickly kind of talk about the different states of operation here. One state is when this guy's not even running. When we put a voltage source on here, that voltage source is going to just go right to the output. We'll have a little drop across these, and that's it. That's one state. The other state is when this guy turns on and this happens. We charge up the inductor, and the capacitor discharges into load, and then the transistor turns off, and then we are back here, and the inductor discharges into the load, like we said. So at this switching node right here, this is the node that goes to ground and back up. So this is our switching node. When on a light load, what we see is this guy drops down, then he turns off and he shoots up high, flies up, so we will see it go up to the voltage level that the output's charged at, because there's just a diode drop. So when the output's, say, regulated at 20 volts, we'll see this go up to 20 volts plus a diode drop. Then on a light load, what we'll see is that waveform will actually drop down to the 12 volts, what we see here, because the inductors ran out of energy, it's discharged. So at that point we just see 12 volts. But what we'll really see is a little ringing here, because when this drops down, there'll be a little ringing between the inductor and the capacitor across, you know, the drainage source of the FET. So it'll kind of ring a little bit until it dampens out, and then, or it doesn't dampen out until the transistor turns on again, then we start over. Okay, so let's go to the waveforms. The first waveform I wanted to show you was, say, a nominal load, where the duty cycle is turning on and off. This is a switching node, so the transistor comes on, so it drops down to 0, then it turns off and bounces back up, so this switch is on and off. And this is would bounce up to our output voltage plus a diode drop, say 20.7 volts. Meanwhile, the current in the inductor is discharging when the transistor is off and charging when the transistor is on. So this mode here, just, I'm saying the nominal load, we're going to say this is really the critical conduction point, the kind of boundary condition where the inductor fully discharges before it turns back on. Right here, it runs out of current and it charges back up. Now let's go to a lighter load. This would be more representative of a light load, or a minimum load. I'm just calling it a minimum load, but a lighter load basically. So this sawtooth waveform is just the same as this sawtooth waveform, except for there's a blank spot, because it's kind of like this. We didn't need this much current, so it's just dropped down. So the duty cycle is less. It charges up and then it discharges. Okay, and then it's flat, because it's run out of current, and then it charges up and discharges. So it just hasn't charged up enough, because the voltage it's regulating is at 20 volts, and it's able to do that without fully charging up the inductor. So we get some flat spots. So this is called discontinuous operation, and this is that boundary condition. It is discontinuous because it's discontinuous just for a moment before it gets charged up again. So this is that critical mode. Alright, but what we're really going to see happen when this thing discharges, let's say right at this point here, it's fully discharged, and right at this point. So when this becomes fully discharged, this voltage doesn't stay up at 20 volts, because now the inductor has run out of current. So this point actually drops down to, say, 12 volts, our input voltage, okay? And so let's just say 12 volts is right here. So it really drops down here and comes over across there. So this guy would have dropped down, whoops, right at this point here, the way I drew that. Yeah, so it's really dropped down here, comes across. So it really dropped down right, let's say 12 volts is right here. So right as the inductor runs out of energy, this thing just drops down 12 volts, and that's our input voltage. So it just drops down to the input voltage. Now it's run out, it's discharged, and we're back to 12 volts. But what I want to say is, really what happens is, depending on the circuit, you'll get some ringing here, and it'll just sit here and ring and then dampen out. But that ringing is because when it turns off, the transistor has a capacitor across it, and then there's an inductor, you know, just sitting there. And so as that inductor capacitor, they start to kind of have a tank circuit, and they kind of ring a little bit. Okay, so we'll see that on the scope. So really, when it drops down, you'll see some ringing. Okay, now let's go to the continuous conduction mode. Alright, so this is the continuous conduction mode. Now let's say this is 0 amps down here. On the scale here, I put 0 amps across here, 0 amps right across here. These points just hit 0 amps before it gets charged. Here, 0 amps is all the way down here. So there's actually a DC current in that inductor all the time, and it discharges down to some point and then goes back up. So this is, you know, a DC level with a ripple on top, and that's continuous conduction mode. So we'll go from here to here in some converters, and sometimes we don't. Sometimes we just go from here to here. So just depending on how it's set up, we might go through these different boundaries, okay? So I put them all here so you can see them. So we can go from this point where, you know, we might operate discontinuous, you know, from maybe here to here, maybe from zero load up to here, and always be in this discontinuous range. Or we can go like in this boost converter, because it operates across such a wide range, we might go from here to something like this, to continuous, okay? And the control loop, like I say, when you go from here to here, it kind of changes, because now you have current in that inductor all the time. It's always charged versus running out of energy and getting to start over each time. So it's really an important thing to understand, the continuous conduction and discontinuous conduction, and then that boundary condition, that critical mode of control, sometimes it's called. Okay, let's go to the circuit setup and then to the scope, and we'll demonstrate this on the scope, okay? We'll hook this up to this load and to the input power, and then we'll look at these waveforms on the scope, and hopefully this will become, you know, more obvious. Alright, so here's our setup. We've seen this a few times, so I'm going to just go over it quick this time. The boost converter, the little loop of wire I have in series with the inductor, and the current's going from this back into the board where that lead of the inductor should be soldered. It's on the other side of the board, of course. So I've got the scope probe on the switching node, and that's our two probes. We're putting out about 20.3 watts right now. Here, I'll show you that in a moment. Input power is coming in here, going into this cable, and then we're reading it with this meter right here so we can account for the losses in the wire here, and so you can actually see what's going on here. So let's just look at it. Right now we're around 0 watts. Let me zoom in so you can see better. Okay, I zoomed in a little closer so you can see the meter, so you can see how the leads drop some voltage. Right now we're 0 watts. I'll show you the minimum load I think we're going to go to, probably right around in, let's go a little bit lower, probably right there, so we can see a nice flat spot right around 23, 24, 25 watts, somewhere around here. 1.3 amps in. And then our critical conduction mode is going to be right, let me see, I'll show you this on the scope in a moment. Just want to show you right around 55 watts, 2.8, 2.75 amps, something like that. And then after that we're going into continuous conduction mode, so we'll go up to say 120 watts maybe. So yeah, so those are kind of the three loads I'm going to show you on the scope. And you can see, by the way, you can see a light load, the input voltage right here, you know, right over here on the cable, this voltage is a little bit higher, and then at max load, you know, it drops down a little bit. So that's kind of why it's set up where I did. So it's right around 12, you know, around the nominal load, 55 watts, it's about 12 volts. That's kind of where I set it. Okay, let's go look at the scope. Okay, I've got the minimum load set up right now, so let's just kind of go over this. First of all, let's just look at the probes. The switching node is channel 1. It's DC 1 meg and 10x. We've got the 20 meg bandwidth limit on it, so it'll clean up some of the noise. And channel 3, we have pretty much the same setup, except for the current probe is set 100x and set at current. Alright, and we're at 5 volts per division, and we start here, so it's 5, 10, 15, 20. So we are boosting. When the transistor turns on, it charges up the inductor. You see it charge, turns off, boosts up the voltage to 20 volts, and discharges the inductor. Then it runs out of energy because we don't have much of a load, and it should be kind of flat here. And this ideally would be 12 volts, the input voltage. And then it turns on and we repeat the cycle again, okay? And this is 5 amps per division, so we go up about 5 amps. This says 10 amps peak to peak because of this noise. So we go, you know, with the noise it goes all the way up to 10 amps. RMS is 2.2, it's about 2 amps, somewhere around there. And there's, you know, that's not going to be quite right because of all the noise and also because it's not flat here. So I think the reason why our waveform on the current isn't ideal looking, like the nice triangle wave and then flat, it is because I looked at the specification, it's only good for 20 kilohertz and we're operating at 107 kilohertz. So it's actually done a pretty good job. It's giving us an idea of what's going on, but the values are going to be off a little bit, okay? So now let's go ahead and bring up the load up, and as we bring the load up you'll see the duty cycle, this on time is getting wider and it's charging up more, so it has more to discharge, but then we still ring a little bit. Right here, the critical conduction point, where now we're pretty much full duty cycle. It might grow just a tad, but we're fully charging, fully discharging, and so that's the boundary mode or critical conduction mode. Now as I increase the load, you'll see this waveform doesn't really change shape, but it'll float on a DC value. So it's starting right here at 0 amps, and you see as I increase it, now we're floating on 5 amps DC. So that's continuous conduction mode. That inductor always has at least 5 amps in it. And the duty cycle, it's a minus width, and it's the on time here when the transistor's on. It's 4.5, and if we drop it down, you see how it stays at 4.5. It drops just slightly, pretty much holds on, and then right there it starts dropping out. It gets a little bit less, you know, lower on time. Not much though. So as I'm doing this, I can see this isn't correct because you can see this is getting narrower, and I think it's reading the value with this ringing. It might be reading up here. It's not really changing much, but we can see that it's changing width, right? But then as right here, the critical conduction mode, where it's fully square, where we don't have the ringing anymore, you can kind of see it doesn't really change anymore. As I increase the load, it just floats up. So there's the 3 modes of operation of that inductor. And right up here, you know, where you have lots of DC and then this ripple's right on top, so that's fully at the input. I've got 12 amps. We're at 100 watt. I'll just drop it down here. So that's what I wanted to show you, and that's a very important thing. Now this ringing here kind of showed that in the lab book, and it kind of talked about that, but this wave shape on this Handtech current probe gives us a nice idea of what's happening, but it's not the ideal wave shape because of, you know, we're operating outside the bandwidth of the probe. Alright guys, so what do you think of that? Kind of interesting, right? Hope you liked it, and I hope that made sense. Like I say, you're going to see more of this. As a matter of fact, I'm going to do another video and release that very quickly here, and it's going to be kind of a repeat of this, but I'm going to actually introduce another piece of equipment, this Tektronix current probe, so you can see something that looks more like my drawings on my notebook, okay? But hey, I hope you like this. I'm trying to demonstrate meters, equipment that we can all use, and so, but I'll show this Tektronix in action next video. So hope you like that. Thumbs up guys, that helps, and see you next time.